that follow a pattern. So instead of writing the whole sum out, we use the Greek letter sigma, summation, as a shortcut. This right here. So the definition says, if we have a positive integer I and assign a value ai for each little I, and m and n are integers with m is less than or equal to n, then the sum of ai from I equal m to I equal n is written as this, as you see here. This means start with I equal m, plug it into ai, and then increase I by 1 each time until you reach n, adding all those results together. Does it make sense? Well, if not, let's take a look at the example. Maybe you think will clear up a little bit. Say, for example, I have summation I equal 1 to 5 of 3i. What I'm going to do is I'm going to plug I equal 1 all the way to I equal 5, right? I'm talking about integer here. And so it'll be 3 times, and then add them all terms together. 3 times I equal 1, so 3 times 1, plus 3 times when I equal 2, plus 3 times I equal 3, plus 3 times 4, plus 3 times 5. Okay, so you add them all up. This will be 9 plus 6 plus 9, 3 plus 6 plus 9 plus 12 plus 15, so that'll be 45. Does that make sense? Makes sense now? Yeah. Now I have summation k from 3 to 7. Sometimes I use k, sometimes I use I. Okay, I want to show you that it doesn't matter what letter you use. The bottom one will be your lower limit, and the upper one will be your upper limit. Okay, sometimes they use k, sometimes they use I or m. It doesn't matter. It's just a placeholder. So we're gonna start at k equal 3. So it's gonna be 5 times 3 squared plus 4. And then 5 times, now start k equal 4, 4 squared, sorry. Oops, I think I wrote wrong, my bad. 5 times 3 squared plus 4, and then plus 5 times 4 squared plus 4, plus 5 times 5 squared plus 4, plus 5 times 6 squared plus 4, and last 5 times 7 squared plus 4. And our final sum will be 695. I had this calculated beforehand. Okay, so that's how we use summation notation. It's just a compact way to write a repeated addition. That's all. So always remember, you start at the lower limit, increase your index by 1 each step, plug in, add up all the results until you reach the upper limit. That's all. Now, number 2 is kind of like reverse engineering. They give you a sum and then you turn it into a summation notation. So here, this one, I have my first value was 36, and my last value is 60. And the way the series go, it looks like it's bumped up 1 unit at a time. So 36 plus 37, 38, 39 plus 40, etc., all the way to 60. So I can write it. So first, I'm gonna write my summation, right? I equal 36. That's my first term, 36, and it end up at 60. And what should be here? Well, I, right? You can just put I there. Don't make it complicated, just I. So I equal 36 plus I equal 37 plus I equal 38, etc. Problem 4, maybe I'll highlight this red, and this one is blue. So this one is, let's see, first I have summation sign, right? And there's a 3, it looks like a 3 here. And I is going to be my index. It's going to be my exponent. Start from 2 and end it at 6. 3 to the I. Right, so I hope you can see the pattern here. All right, and last one. This one a little bit harder to recognize. If you're one of those very smart students, you probably could recognize this is a factorial. If you work with factorial a lot, you can see 0 factorial. So this I can rewrite it as, I'm going to use green here. So this one is, say, 0 factorial plus 1 factorial plus 2 factorial plus 3 factorial plus 4 factorial plus 5 factorial, etc. It looks like this one without bound, so let's go to infinity here. So 0 factorial by convention is 1. Don't ask me why. 1 factorial is 1. 2 factorial is 2 times 1. Right? It's still 2. 3 factorial is 3 times 2 times 1. So 6. 4 factorial is 4 times 3 times 2 times 1. So 24. And on and on. So I can write my summation like this. I equal from 0 to infinity, because it looks like it doesn't stop anywhere. I factorial. Or let me do n. You can go with n. No, I is fine. I is fine. You can do because I'm starting with yeah, I is fine. Just notation. Okay. All right. For finite sums, we have the following properties. The first one will be the constant c. So if I have summation k equal 1 to n, and then the constant c, remember it's just a constant, it's not a variable, not like you can plug k in, right? Notice this is k, this is c. So c stands for constant. Then basically you add in the same number c n times, right? So that means the same thing as say c times n. The second one, I have summation k equal 1 to n of k, right? We just did it here. Actually, we just did it right here. So instead of using I can just use k, right? So basically you add k n times. No, not. You bump up k 1 unit at a time, right? And we have handy dandy trick here. If you have 1 plus 2 plus 3 plus 4 all the way to plus n, then it's equal to n times quantity of n plus 1 divided by 2. I recommend you use a formula. By the way, there's a history attached to this formula. Look it up. Maybe many of you already heard of it. The square one, summation k equal 1 to n k squared. Or sometimes you use I, same thing, right? Then it means 1 square plus 2 square plus 3 square all the way to n square. Then the shortcut will be that formula. And then the last one will be the cube one, summation k equal 1 to n k cube. Then we have this shortcut. You are not expected to memorize these. It will be given to you if I ask you something like this, okay? Now, for linearity, if I have a summation of a constant times a series, then I can move the constant outside the summation and times to that sum. Okay. The second one, if I have a sum of a summation, then I can split them up, become individual summation. Right? Same thing with the difference. I can split them up. But what it does not work is if you have a product of a summation, it does not split into two products. Okay, it just does not. It doesn't work like that. Same thing with quotient. You can try it out. So example will be maybe the example. You can try the example for the summation k equal 1 to say to 2 of n times n plus 1 perhaps. It is not equal to summation k equal 1 to 2 of n times summation of k equal 1 to 2 of n plus 1. It is not, right? You can play out yourself. Because the left side was 8 and then the right side was 15. This is definitely not equal to each other. You can similar with the quotient rule. All right, let's take a look at this example here. I have summation k equal 1 to 875 of 10. Right, so this is a constant one, right? So what I can do is add up the 10 875 times, or it's the same way of saying 10 times 875, which is 8,750. So this is a constant rule. The second one is going to be the difference of sums, right? We can split it apart. So first I will write it as sum k equal 1 to 200 of k minus summation k equal 1 to 200 of 100. For the first sum, we're going to use this rule. Now you're going to use that rule. So you add in, so you start from k, so 1 plus 2 plus 3 all the way to 200. But instead of doing that, we're going to use this one, right? So here n is 200. So 200 times 200 plus 1 divided by 2. So for this one, it's going to be 200. Okay, n is 200. 200 and plus 1 divided by 2. And then for the second summation, it's going to be a constant rule because 100 is a constant. So 100 times 200. Add up 200 times. Happy ending will be 2,000 minus 20,000 will be 100. 2,000 minus 2,000 will be 100. Proceed again. First thing first, I'm gonna split it apart because there's some here. Linearity is okay. 3i squared plus sum I equal 1 to 20, 2i squared. Remember the next step, because 3 times I squared, the 3 is a constant, I can pull it apart, right? Remember this rule right here, I can pull the constant to the front. I'm gonna do step by step here. So it's gonna be 3 summation I equal 1 to 20i squared plus 2 summation I equal 1 to 20i. For I squared, we have this rule, and then I, we have this one. Right, so we're going to scroll up and down quite a bit. And n plus 1 to n plus 1. Here n is 20. 3 times, times 20, and then 20 plus 1. 20 times 2 plus 1, is that right? Yep, divided by 6. Plus 2 times n plus 1, so 20 20 plus 1 divided by 2. Yep. Divided by 2. I'm gonna give you a happy ending. Will be 9,000 and 30. Last one. Now, what I don't want you to do is split up this and this. Remember that? Remember we're talking about this. The linearity is okay, but we don't have product and quotient rule like that. So you can't split them up. So what can we do is we're going to distribute, right? Maybe we can distribute the 1/50 to each of these components. So we have sum k equal 1 to 100. Let's distribute. So 3 times 1/50 minus 1/100 j square times 1/50. Now we can simplify. We can do step by step. We don't have to do all of it. So, oops, let me put a big parenthesis here. And now I can split it apart, right? Let's simplify first before I actually split it apart. I like to simplify things. Come on. Summation k equal 1/100. 3/50. We can do much. But this one is j squared over 50 with 500,000. 100 square is 10,000. 10,000 times 50 is 500,000. All right, now we can split them. Summation I equal 1 to 100. 3/50 minus summation I equal 1/100. By the way, I'm going to pull out the 1/500,000, okay, because it's constant. All I care about the j, that's the variable. So yeah, move this up, move this to the right a little bit, so I can 500,000 j squared. Okay. Now this the first one is the constant rule, right? It's gonna be 3/50 times n. N here is 100, which is 30 divided by 5, which is 6. Okay. Minus 1/500,000 times j squared. So this rule right here, this one, that one, it's gonna be n plus 1 to n plus 1 divided by 6. So n is 100, so n 100 plus 1, 2 times 100 plus 1 divided by 6. And this part here is 338,350. I plug it in. Well, it's just simple operation here. I'm going to give you a approximation. The final answer is 5.3233, something like that. Not important. Just give me an approximation.